So this is section 1.4, collecting data to understand causality. So often the most important questions in science, business, medicine are questions about causality. In other words, does smoking cause cancer? Will eating an apple a day keep the doctor away? Will taking medicine make me feel better? Does studying a foreign language improve a person's verbal skills? If someone claims that the answer to any of these questions is yes, then how do we know whether to believe their claim? So we need to look at some pieces here so we can talk about how we could do a study about these questions. Notice that two variables are given in each of the following questions. And here we are going to identify the variables. Feel free to press pause on your video and try to work ahead and then continue playing your video. So, does smoking cause cancer? What are the two variables um, in this research question? So, one would be, do you smoke? And the other would be, did you develop cancer? Will eating an apple a day keep the doctor away? So, do you eat an apple every day? How many visits to the doctor? The way the variable is phrased will tell us what type of variable we have. So in do you smoke, we'd be looking at a binary. Yes, no. Did you develop cancer? Yes, no. Binary. But how many visits to the doctor may be quantitative or numerical because we'd be giving the number of visits maybe over the course of a year. Will taking this medicine make me feel better? Did you take medicine? Did your health improve? Does studying a foreign language improve a person's verbal skills? And will doing my homework this semester improve my grade? So did you do your homework? And the other variable would be your grade. So most questions about causality can be understood in terms of two variables. We call these variables the treatment variable or the explanatory variable, and the outcome variable referred to as the response variable. These questions are essentially asking whether the treatment variable causes changes to the outcome variable. So we're going to go back up and look through these variables and identify which one is our treatment and which one is our outcome. So, do you smoke? That would be the treatment. Or the explanatory variable. And did you develop cancer would be your outcome or your response variable. Will eating an apple a day keep the doctor away? The apple variable is our treatment, and the number of doctor visits would be our outcome. Does taking the medicine make you feel better? So the medicine treatment, your health outcomes is your outcome variable. Does studying a foreign language improve your verbal skills? So studying a language would be your treatment, and your outcome variable would be your verbal skills. Will doing my homework this semester improve my grade? Homework is your treatment or your explanatory variable, and your grade is your response or outcome variable. So let's consider one of these questions and talk about what we would need to conduct a robust study. So, will eating an apple a day keep the doctor away? If you recall that one of your high school friends ate an apple every day and never went to the doctor, was never sick, would you conclude that eating an apple caused this person's good health? Probably not, right? This is a specific example of anecdotal evidence. An anecdote is essentially a story that someone's telling you about his own experience. And people are always willing to share their anecdotes. So we have to listen to them with caution. Anecdotes are not very useful for answering a question of causality. And why is that? Probably because there's so much variation in people, we wouldn't know specifically if it was the apple that caused the person to be in good health or something else. They might have just been, have good genes, or maybe they exercise a lot. So we cannot determine causality from anecdotal evidence. But what if a study takes a look at a group of people and asks them whether or not they eat um, apples regularly and whether they visit a doctor? Is this better or worse than anecdotal evidence? Well, this would be better, but still not perfect. Um, so notice that this is an improvement because we have a comparison group. And people who eat apples are being compared to people who do not eat apples. And the people that eat apples are in the treatment group, we would say, because they're receiving the treatment of interest. In this case, it's they are eating the apple. And the people who do not eat apples are in what we call the comparison group because they do not receive the treatment. And we call this comparison group the control group. So the study in number 6 is referred to as an observational study. And so this is one type of study that we are looking at. Subjects in an observational studies are put into either treatment groups or comparison groups by their own action. In other words, they're already doing it. This is just the way things are. And then someone comes along and decides to do a study and just observes what is going on. In other words, they do not do anything to tell the people whether to eat the apple or not. They're just observing whether they did eat an apple or not. And so an observational study, the person running the study is just observing what is happening. If people in the observational study show up that they're generally healthier than the people who don't eat apples, can we conclude that eating apples causes better health? So it might be tempting to be like, oh, that's pretty strong evidence. but we still can't conclude that it's the apple alone causing this because we don't know what other variables may also be out there. So may cause good health. So let's look at the next page. And can you think of any potential differences between the treatment group, so the people who are already just choosing to eat apples, and the comparison group, people who don't eat apples, that might explain why the treatment group was healthier? And so people who choose to eat apples may have a healthier lifestyle. They might eat healthier. And they may exercise more. So these types of variables that we're listing here are called confounding variables. A confounding variable is any difference between the two groups other than the treatment group that it could explain why the outcomes are different. So can you think of possible confounding variables for this study? And really, I listed them here. People who are already choosing to eat apples may be eating healthier in general. They may be more likely to exercise, and those other variables may be what's actually causing their better health, not just eating the apple. So these are called confounding variables. And the major drawback to an observational study is that you can never know whether a confounding variable exists, which means that we can never conclude cause and effect relationship between treatment and outcome. Okay, so we can say that there's an association between eating an apple and good health, but we cannot say cause and effect. So this is the number 12. We want to star. This is a very important conclusion that observational studies never conclude cause and effect. As soon as you see a study is observational, you know that you cannot conclude cause and effect, no matter how tempting it is. You can just say that there's an association. Consider a study that takes a random sample of people and then randomly assigns half of them to eat the apple and the other half not to. A researcher then follows them for a year and sees who visits the doctor. How might this be better than an observational study? So we're random sample of people and we're randomly assigning them to groups. So, and asking half of them to eat the apple. So we might be evening out confounding variables. In other words, we're asking people who may have a healthy lifestyle to eat apples and who may not have a healthy lifestyle to eat apples. So the study in 13 is referred to as a controlled experiment. So this is another type of study. The first one we looked at was observational studies. The second study we're looking at is a controlled experiment. In a controlled experiment, researchers take control by assigning subjects to their two groups. So in an experiment, the researcher is doing something. They're assigning the subjects to groups and telling who's getting the treatment. If this assignment is done correctly, it ensures the two groups are nearly identical in every other way except whether or not they receive the treatment. If we can make sure that the two groups are identical in every way other than the treatment variable, then we can conclude a cause and effect relationship. So controlled experiment, well done. You can conclude cause and effect. Okay? So can you think of a way to assign the subjects to two groups to ensure that the two groups are alike in every way? So the best way to do that would be to do this randomly. All right. A good controlled experiment uses random assignment. Random assignment is talking about the people who are in the study being assigned to one of two groups to either receive the treatment or not receive the treatment. And this can be done in many ways using coins, a random number table, or technology. The most important thing is that no human determines the group assignments. Humans are not good at random assignment. The goal of random assignment is to balance the group so the variation in diets, weights, heights, ages, etc., and all the stuff we don't know, any background variables, is even between those two groups. And this helps minimize a bias. And bias indicates that the results of the study are influenced in one direction. Random assignment is what we need to make a proper experiment. So note that random assignment is different from random sampling, okay? We both have random. Random assignment is grouping the people once they're already a part of the study, where random sampling is picking the people to come to be in the study. A study may use both random assignment and random sampling. They may use one or the other or neither. Random sampling refers to how the subjects are selected for the study, and random assignment refers to how the subjects are assigned within the two groups. Why do you think random sampling is important? So this would make good random sampling would make your sample representative of a population. And it would reduce bias. What does the use of random assignment allow the researchers to do with the results of the study? So the first question was about random sampling. This one's about random assignment. This allows, random assignment allows causation, you to conclude causation. Causation. What does the use of random sampling allow the researcher to do with the results? So again, now we're looking at sampling, random sampling. This allows us to generalize our results to a population. Another question that researchers are interested in is whether or not the results of their study can be extended or generalized. So, can we take the results from their sample and extend it to a larger population or maybe even the whole world? And this depends on how the subjects were selected. So, if random sampling was used, then the results may be extended to the population that the sample was selected from. In studies where random sampling cannot be used, which does happen, researchers often try to replicate their findings with additional studies and more diverse groups of people. So, if cause and effect conclusions are only possible with controlled experiments, then why would we even do an observational study? Seems like the observational study isn't that helpful. So one thing to consider, and if we look at this hint, think about the study looking at whether smoking causes lung cancer. Why would we not want to do a controlled experiment if we were looking at smoking and lung cancer? And the simple answer is that we cannot randomize people to smoke, right? We can't make people smoke. So really there's ethical reasons for why we would need to use observational studies.